Y'all get it yet? Y'all know what you're doing? Anyone have a question?
Question.
Yes.
You use a sign theorem from the cross product in order to solve this, and then we're solving this, correct? Assuming you're looking for the angle and you use the...
You do not need to do that. I would not do that. Okay, so let me ask you something. If I gave you two vectors, could you find the angle between them?
Yes, sir.
Using what? Last class, we had a formula. Do you remember that? Yes, the dot product version would be the cleaner way to go. Okay? So we first have to agree that the angle between these two planes' normal vectors is equivalent to the angle between the planes themselves. Yes? So as long as we agree with that, then all you have to do is find the angle between the two normal vectors. So what is the normal vector of the first plane? I'm going to call it n1. It's the normal vector of the first plane. 1, 1, 1. So you're just pulling the coefficients. What's the normal vector of plane 2? 2, negative 4, and 7. All right? And now you just need to find the angle between them. So using the formula from last class, we had that theta was equal to the inverse cosine of something, and that was it was u dot v over the magnitude of u times the magnitude of v. So for us, it'll be n1 dotted with n2 over the magnitude of each of those. So that's what we're going to use. Is that what you did? Did you get an angle? 67.5 degrees, right? So you did that in degree mode? Okay, anyone else get that? So anyone get something different? You look like you, huh?
I didn't have a calculator.
Oh, okay, I'm sorry, I saw your thing. Did anyone else get that far? No?
Well, it's close to like 69.
There might have been some rounding in there. I don't know. Let me see. Did you type it all in at one time? Yeah. And you have root 3. Let me just root 3 and then root 4 and 16. What about this right here? Magnitude of this one should be 4 plus 16. That's 20 plus 49. I think that might be it. Did you put 57? Right? Because this should be 49.
Should be square root of 69.
It should be square root of 69. I think you just did arithmetic there. Yeah, no big deal. Okay, so 69.7. Okay. All right. So I'm going to continue. I'm going to move on, but just make sure you can get that on your own, that angle between those two. I'm gonna kill the lights just a little bit. Since you're already tired, I'll help you out. Just finish you off here. All right, so tell me if you agree with this. If you have two planes that are not parallel, okay, so they are not parallel to one another. If you have two planes that are not parallel, that they must then intersect each other. And what geometric object would they intersect at? It would be a line, right? So two non-parallel planes should intersect at a line.
Yes.
And maybe we can come up with the equation of that line, right? I mean, if they hit at a line, we just spent the last part of class talking about the equations of lines. So if you have two planes and you want to try and figure out that line of intersection between the two planes, then here's how we can do it. First, we can just say, all right, we know the normals of these planes, don't we? We know they're normal vectors. And since they are vectors, we could imagine sliding those normal vectors down to that line of intersection. So all I've done is I've taken the normal of each one, slid it down to the line of intersection. And what I'm going to do now is cross those two normals. When I cross the two normals, that cross product should be pointed in the same direction as that line. Does it make sense that it would do that? So two planes, they intersect one another. I take their two normals, I cross them. That gives me a new vector, which is the direction of the line of intersection. So there's only one more thing I need to define the line. What were the two things you needed to define the vector equation of a line? A point and a direction vector, right? Or 2 points. In this case, I'm going to just use the cross product of the normals to get the direction, and then all I need is 1 point of intersection. All right, that kind of makes sense? So find the vector equation of the line of intersection of these two planes. Those are the same two planes we were just messing with, right? So let's find the vector equation of the line of intersection. So I'm going to take the normal of the first one, which was 1, 1, 1. The normal of the second one, which was 2, negative 4, 7. And I'm going to cross the two. When I cross these two, I get, so this one I think I can handle. 7 add 4, so 11. And then 7 take away 2, it's 5, but change the sign, negative 5. And then last, I have negative 4 take away 2, so negative 6. So I've taken my two planes, I've crossed their normals, that gives me this, and this is what part of my line? What is this part? That's the direction of my line. So we called that V earlier, didn't we? So that's going to be my V on my line. And remember, I'm trying to get to this. I'm trying to come up with the vector equation of my line, like this. Right? So that was my goal, is I need to come up with the equation of the line that represents the intersection of those two planes. I'm able to extract this direction vector by crossing the two normal vectors. And now all I need is R naught, right? Which is any point on that line, right? Any point that you can come up with that lives on the line of intersection of those two planes. And how in the world would I find that? I need you to tell me a point that lives on both of these planes. Any point. So aren't you just trying to come up with an X, a Y, and a Z that makes that true,
Yes.
while simultaneously making this one true?
Yes.
Right?
Do a matrix here.
You could do a matrix here, yeah. So
You could just make a
I could do, so I'm trying to do this. I'm trying to solve this system of equations. But the problem is, I guess it's not a problem, it's actually a good thing, is that I have more unknowns than I have equations, which means that I'm going to have infinitely many solutions. And so I should just do what we did before when this happened. Just fix one of them. Like just pick a value for one of them. And I like to, just my preference, I like to just let z be 0. I don't know why, I like to do that. If z is 0, then what do these equations become? X plus y is 5, and the other one is 2x minus 4y is 10, right? It becomes this new system, which is just a 2 by 2 system, which is much easier to work with. My z is fixed, and we can use substitution or Gaussian elimination, right? So again, I'm just a fan of Gaussian elimination. I'm just going to do -2 on the top one. -2x minus 2y equals -10. Rewrite the second equation, don't change it. Oh, what do you get here? Yeah, you should get y is 0 here. The x's cancel, you get -6y equals 0, so y is 0 here. So I'm going to just put that here, y is 0. So if I know z is 0 and x is 0, if y is 0 and z is 0, then I can go back to this and get x. X must be then 5, right?
Yes.
Okay. And that works in both equations. So the point that I can use, right, for my R naught, the point that I can use is the point 500. Right? That point right there lives on the line of intersection. And you could have done this, and you could have let x be 0, y be 0. You could have let z be 10. It doesn't matter what you use here as long as you go get a single point off that line. So now, final answer, I need this equation written out using the point and the direction vector over there. So this becomes R naught 500 plus t times v, and v was 11, -5, -6. And I'll put it all together, 5 plus 11t, and then -5t, and then -6t. And t here is an element of the real numbers. So there it is. Any questions on what I did there? Please make sure you know how to find the line of intersection of two planes. That's an important part of what the things you need to be able to do in here. You know, these are very, very long classes, and I feel bad for you. But the good news, I mean, we only actually are, meeting 16 times, you know, and one of those is the final, and another one is like half a test, so it's really only 14 times, kind of. And we almost have 2 of them out of the way. So I just keep looking at the clock. I'm like, golly, I can't believe how long it's taking for 5:30 to get here. Is it 5:30 or 5:40? What do we go to? 5:30. You sure it's not 5:45? All right. Now I realize we only have 15 minutes, and I realize it's been a long day, long week, whatever. But this is an important part of this section right here. These distances. And which one are we going to do first? Okay. So if we have, again, like let's take the projector as being a point, right? And then we have some arbitrary line. Would you mind holding the line? Put it wherever you want. Not there, though. No, not there. Anywhere, but no, not there, though. I'm just kidding. There you go, okay? So there you go. We have an arbitrary line and an arbitrary point, right? What is the shortest distance between that line and that point? Yes?
It's going to be like a line perpendicular to that includes that point.
Okay, so where would that be in the room? Let's see. Okay, so imagine extending, so you're going to hold that, we're going to extend this line out somewhere around here, and you're saying that there's like a perpendicular that goes to that?
Perpendicular to that.
To this perpendicular to this line that goes up to that. Do you all agree there's like a shortest distance somewhere?
Yes.
Okay, thank you. Good job. So how do we find that? Doesn't that seem somewhat challenging? Again, because we're in three-dimensional space, if you do this on a flat sheet of paper, it's a different story. But in three-dimensional space, just give me an arbitrary line and then try and figure out where this line is closest to that point. Seems difficult, yes? So here's how it's going to be done. Wait a minute. Yeah, I did the other one first. It's okay, we can do this one. Okay, so imagine we're in three-dimensional space. I know it doesn't look like it from here, but imagine that we are in three-dimensional space, all right? So we have a line and we have a point. And we've kind of moved ourselves around in the room, so we're looking at it and it kind of looks like that to us from our perspective, all right? So what if we did this? We picked 2 points on this line. So we have the equation of the line. It's been given to us. So we should be able to generate any 2 points we want, right? Then we're going to draw a vector between those two, vector A. Then we are going to generate another vector B that goes from one point up to our point P. We should be able to do all of those things, right? We have the equation of the line, we have the point, we should be able to generate all of this information. Now, what we're interested in is figuring out that distance, right? But look at this. This is just a pretty simple trig problem. If theta is the angle between them, then sine of theta is just that distance, right, divided by this magnitude. So sine is opposite over hypotenuse, right? Is this what you were alluding to earlier? Okay. I had a feeling that's what you were saying. Right? So that's what it would be, right? That's and then we could solve for D. Right? So D would be what then? D would be the magnitude of B times sine of the angle between the two vectors, right? Does that seem like a pretty easy construction? So someone gives us a point. Right now, here's what we would need to do, just according to this. Someone gives us a point, someone gives us the equation of a line. We would just need to find the magnitude of B. What's the magnitude of B? The distance from any point we want, right, to the point we're given. Take the magnitude of that vector, and then what will we need? The angle between these two vectors. So we would have to do this, and then we'd have to go find the angle, kind of like the previous problem where you did the arc cosine. So it's going to be a little tedious, isn't it? A little tedious? God, I really do wish that right in front of this was magnitude of A. God, if it was magnitude of A in front of that, then what is that? If the magnitude of A was in front of this, what is that? Not the dot. It's the magnitude of the cross product, right? If the magnitude of A was there, then that would just be the magnitude of the cross product of those two vectors, wouldn't it? Yeah. So it's not there, but it would be nice if it was there. So I'm just going to make it be there, but not quite. So I'm going to make it be there, right? And then I'm going to divide by it, right? Right? Yeah. And then that's just the magnitude of the cross product of A and B over the magnitude of A. Just enough time to finish class. Isn't that what that would be? So geometrically, it was that, which we could do, but we would then have to go and do our cosine and all that, right? And we'd actually need the angle to do the problem. But by just realizing that this is almost the magnitude of the cross product and multiplying and dividing by this, we actually get a formula that requires no angles at all, right? You're going to have no angles in this formula. All you need to do is cross these two vectors, find their magnitude, and divide by the magnitude of A. Pretty nice, right? So scrolling down here, this is basically me saying that, and you get to this right here, right? Now, does anyone have any ideas of an easy way we could get this vector A? Other than someone giving, like us going and finding 2 points? Like if somebody gave you the vector equation of the line, right? Somebody gives you the vector equation of this line. What's another thing I could use for A?
The direction.
The direction vector of the line, right? Remember the V? The V is the direction vector of the line, isn't it? So why don't we just use the V for this vector? And then all we really then need to come up with is the vector connecting these 2 points. Okay, so let me re-illustrate that with an example. Let's find the shortest distance here between this point, 3, 6, negative 7, and a line that goes through those 2 points. So I'm going to draw my picture here. I have my point up here, 3, 6, negative 7. And then I have a line that has these 2 points, 0, 3, 5, and negative 4, 9, 10. What is the shortest distance between this point and this line? I only need 2 vectors to do this, right? That's all I need. 2 vectors and I'm done. One vector that I need is the vector, any vector on this line, right? That vector right there would work. So what's that vector? Negative 4, 6, 5, okay? Then I need another vector. The vector that goes from where to where? Yeah, any point on that line to the point that we're trying to minimize or get the closest to, right here, okay? So this one is the vector 3, 3, 2. I believe that's a 5, right? Yeah. Oh, no, negative 12. And now we can just go straight to the formula. Yes?
Can we not just use the component formula?
The component, can we just use the component formula?
Do a vector projection?
That is an excellent question. What do y'all think? We're trying to find the distance from here to here, right? We have this vector and this vector. You're saying, can't we just use the component? So where is that? The vector you're talking about, the component, where is that here? Which vector are you projecting onto which vector?
Projecting the orange vector onto the blue vector.
This one onto this one? Okay, so when I project that down, oh,
It passes over.
the class is over. Yeah, it pretty much is at this point. But if I project that down, right, I want this distance, right?
Yeah.
The component, remember, is the projection vector is there. This to here, it's that length, right? So you want this length. So not quite, not quite. What was I asking, though? Was I asking something else? We have our 2 vectors, right?
Yeah.
I mean, we're there. We just need the formula now. The formula says that this is D. So D is equal to, it was what? A cross B over the magnitude of A. But which one was A and which one was B? Be careful here.
A was the bottom.
Yeah, A is this one and B is this one. I think you could handle that? Yes? Take these 2 vectors, cross them, take the magnitude, and then take the magnitude of A and divide it through, and that's your minimum distance. All right. Yeah, so my computer's quit, and I guess we're quitting. Everyone have a good weekend, and I'll see you on Monday. We have one more thing on distances to do, and then after that, we jump into quadratic surfaces, and then calculus stuff starts.